Hi everyone, so in this video we are going to solve another problem related to eigenvalue analysis, and what is asked to do here is to find the first order perturbation, meaning just one term in the expansions that we are going to derive for the eigenvalues of the matrix. Okay, only eigenvalues, no eigenvector in that case, of the matrix which is given by this diagonal matrix E1, E2, E3 plus a skew symmetric matrix. You see that the transpose of this matrix is equal to, the lower part of this matrix is obtained as negative times the upper part of the matrix, all right? So meaning that the transpose is equal to negative the original matrix. All right, so, and we are required to determine the eigenvalues, the asymptotic expansions of the eigenvalues only when the AIs are either large, either small. All right, so this is clearly a problem that is stated in the form of what we have seen to tackle eigenvalue problems. So we can start with small values for AIs, so A1 and A2. And in order to formalize this, what we can write, or what we could write, is that A1 is equal to epsilon alpha 1, and A2 is equal to epsilon alpha 2. All right, there was no epsilon in the statement of the problem. All right, so we need to introduce ourselves the small quantity in this solution here. Okay, where epsilon is a small number, and we assume that alpha 1 and alpha 2, both of them, are quantities that are of order 1. All right, so if we rewrite the problem in this way, let's probably introduce new symbols as well. That will be easier. So let's just write M0 is equal to E1, E2, E3. All right, so this first diagonal matrix, and M1, which would be 0, alpha 1, alpha 2, minus alpha 1, 0, alpha 1, minus alpha 2, minus alpha 1, and 0. All right, like this. So we need to solve. So we need to solve M0 plus epsilon M1 minus the eigenvalue lambda times the identity matrix times the eigenvector phi is equal to 0. All right, this is a 3x3 problem, so we do expect 3 different eigenvalues. All right, and so what we can start with is regular expansions for the eigenvalues and the eigenvectors. So I'm just going to write lambda is equal to lambda 0 plus epsilon lambda 1, and so on. And phi is equal to phi 0 plus epsilon phi 1, and so on. Probably we could just have a look at what we're going to get if we keep another term in the sequence, all right, here. So let me just add epsilon square lambda 2 and epsilon square phi 2 over here, all right. So what we then do is to just plug these two expansions in the original problem. So we have, let me just write it in 2 steps, M0 plus epsilon M1 here minus lambda 0 I minus epsilon lambda 1 I minus epsilon square lambda 2 I, and all of this is multiplied by phi 0 epsilon phi 1 plus epsilon square phi 2, and we definitely have left things that are of order epsilon to the third. All right, so we need now to collect the terms having the same orders of magnitude. All right, this has now become quite usual. At leading order, we'll have this and this. We have here minus lambda 0 I identity, so m0 minus lambda 0 I is equal to phi 0. Okay, is this expected? Yes, of course, as usual. This is nothing but the original problem. You see here, it's nothing but the original problem in which we have just discarded epsilon. So this is the unperturbed problem. Okay, at the following order, so we'll have minus lambda 0 I multiplied by phi 1. All right, for sure, because we, instead of multiplying here by the first term, we do just multiply by the second. And so we need to add on top of that everything here which is of order epsilon multiplied by the leading on the right in the second factor. So we'll have plus m1 minus lambda 1 I multiplied by phi 0. That needs to be equal to 0. And we can keep going to the following order, where we're going to have m0 minus lambda 0 I times phi 2 this time, plus, okay, on the left, in the first factor, things that are of order epsilon. All right, so we're going to have this and that. We need to multiply by phi 1 on the right. And then we need to keep things of order epsilon square on the left and order 1 on the right. All right, so that's going to be minus lambda 2 times the identity matrix times phi 0. And this is equal to 0. And we keep going. You can keep going this way. Okay, so the reason why I wanted to go to order 2 is just to show you that no matter where you go, the problem will be always conditioned by the same operator. All right, so at leading order, we need to solve the unperturbed problem. All right, so let me just now look at the solutions at each order separately. m0 minus lambda 0 I times phi 0 is equal to 0. So this is a standard eigenvalue problem. How do you solve this one? You start first by getting the eigenvalues. In order to get the eigenvalues, you just need to write that the determinant of m0 minus lambda 0 I is equal to 0. All right, so let's try to solve this. Oh, that's quite simple, in fact, right? Because you see m0 is over there. This is E1, E2, E3 on the diagonal elements. And so it means that m0 minus lambda 0 I actually is nothing but E1 minus lambda, E2 minus lambda, E3 minus lambda. And this is equal to 0, so it means that lambda is equal to E1, E3, or E2, sorry, or E3. And so we have it. All right. So that's the first order perturbation of the eigenvalues of the matrix. Well, this is not the first order perturbation because this is the leading order solution. So, but still, this is the leading term, and we can have a look at the first correction. All right. So the first correction that we are asked in this question here is lambda 1. All right. So it's not necessarily a two-term expansion that we are seeking, because if lambda 1 was equal to 0, the two-term expansion would be lambda 0 plus nothing. So we would have to go to lambda 2, all right? So the way to say the first perturbation means that we stop at order epsilon. So we need to compute lambda 1. And so, of course, clearly this is lambda 0 on the diagonal here. and we need to keep going. So before going a little bit further, what we need to do is to compute the eigenvectors, all right, corresponding to the eigenvalues, eigenvectors. So how does it work? Well, you just take them one at a time. Lambda 0 is equal to E1, and then you subtract this value for lambda out of the original matrix, and you solve the remaining problem, all right? So let's see what it gives. So we have E1 minus E1, that is 0. So we have a full line of zeros to start. Then we have E2 minus E1, then 0, 0, 0, E3 minus E1, all right? And we want to solve this times phi 0 is equal to 0. All right, so you see that the solution of that equation is clearly something for the first component, which is chosen arbitrarily. You can put anything you want because it's going to be multiplied by 0 anywhere, okay, by all zeros anywhere, anyway. Sorry, here. And then just pick zeros for the other components, all right? Because if we assume that E1 and E2 are different, and E1 and E3 are different, then this forces us to choose a 0 over there. All right, so that is the first, sorry, this is phi 0. This is the first eigenvector corresponding to eigenvalue E1. If we do the same, the second eigenvector corresponding to eigenvalue E2 is going to be 0, 1, 0. And the third eigenvector corresponding to E3 is going to be phi 0 equal to 0, 0, 1. All right, like this. I assume it's not necessary to go through the details. Okay, so once this is done, we can go to the following order. And so at order epsilon, we have to solve m0 minus lambda 0I multiplied by phi 1 is equal to minus m1 minus lambda 1 I multiplied by phi 0. All right, so at this stage you should remember what to do and how to do. So we should make sure we do project that equation in a direction that is perpendicular or orthonormal to this matrix, which is singular, and this will allow us to determine lambda 1. All right, so what sort of projection do we choose? Of course, we do a projection of phi 0. All right, why do we do this? Because this matrix is symmetric, right? The matrix here is symmetric, so it means that the eigenvalue on the left is the same as the eigenvalue on the right. So if we multiply this by phi 0 transposed, of course, here on the left-hand side, we do this just to make sure we obtain 0. And on the right, we'll get minus phi 0 transposed m1 phi 0 plus lambda 1 phi 0 transposed phi 0. All right. So this needs to be computed in all three different cases, right? So, but no matter the case that we are looking at, 1, 2, or 3, the squared norm of phi 0 is equal to 1, okay? And so it means that lambda 1 is equal to phi 0 transposed times m1, which is over there at the top, all right? So let me just copy it so we can expand the computation. Okay, we have minus alpha 2 here, minus alpha 1, 0, plus alpha 1, 0. And we multiply this again by phi 0. All right, so these are vectors. Vector and a vector. All right, so at the end of the day, of course, lambda 1 is a scalar. Okay, so, and we're going to realize right away that this simplifies. So for instance, if phi 0 is equal to 1, 0, 0, okay, which is the first eigenvector, you see that when you compute this product here, what you end up with is 0 times 1 plus zeros. Then we have minus alpha 1 plus zeros. Then minus alpha 2 plus zeros. And we need to multiply this on the left by phi 0 transposed. All right, that's a dot product, and the result is equal to 0. All right, we can replicate and do the same for the other eigenvalues. And if we do the same for the other eigenvalues, so that's eigenvalue 1. We have eigenvalue 2. All right, let me just clear this off because that's probably too detailed. Eigenvalue 2 will provide lambda 1 is equal to phi 0 transposed multiplied by m1 minus alpha 1, 0, alpha 1. Okay, which I copy like this and multiplied again by the eigenvector. So we see that this quantity here is equal to, well, the central column, easy, right? Alpha 1, 0 minus alpha 1. And if you multiply by the first vector, again, you see this is 0. All right, so the first perturbation to the first two eigenvalues are, both of them are equal to 0. And I bet you know where we're going with the third, because the pattern is quite symmetric with the three different eigenvalues. Let me just write it in short like this, 0, 0, 1. And we understand that this time we're going to keep the third column in M1, which is alpha 2, alpha 1, and 0. And therefore, the product is also equal to 0. All right, so the first perturbation to the roots is equal to 0. And then we can just claim that when A1 and A2 are small numbers, then the eigenvalues, lambda 1, lambda i's, let me just write lambda i's with I is equal to 1, 2, 3, referring to the three eigenvalues, are just ei plus 0 times epsilon plus order epsilon square. All right, and let's close it over here, and let's just have a look at the problem now when the AIs are large numbers, okay, which is probably something a little bit more interesting. So instead of having small values, we're going to take large values. I will copy this momentarily so that we have this with us. All right, so large values for A1, A2. All right, so the problem doesn't specify whether A1 is much larger than A2 or both of them should be larger, but it doesn't specify how large they are. So I will just assume that A1 and A2 can be written in the form of something that is of order 1 over epsilon. All right, so I'm going to rewrite them this time alpha 1 over epsilon, and A2 is alpha 2 over epsilon. All right, this question is borrowed from the book of Hinch, I repeat, which is a great document that you should definitely read if you want to learn more about perturbation methods. All right, so let's then rewrite the problem, and we can keep using the same notations as those we had earlier. So if we use these matrices here, copy and paste. All right, I didn't paste. Sorry. So let's copy this. All right. Great. So again, if we introduce these matrices, then we see, in fact, that in the original problem, that matrix with our current notations will become 1 over epsilon multiplied by m1. All right, so we need to solve m0 plus 1 over epsilon m1 minus lambda I is multiplied by phi is equal to 0. All right, so that's what we need. That's what we need to solve. Cat. All right, so because we don't like to divide by small numbers, what we do here is that we multiply, of course, left and right by epsilon. So in other terms, we want to solve, I will just also reorder the different terms. We need to solve epsilon m0 plus m1 minus epsilon lambda times I times phi is equal to 0. All right, and so what we could do is probably redefine this, because we see that in the unperturbed case, okay, that's something we should probably observe here, unperturbed case just means m1 times phi is equal to 0. All right, and m1 times phi is equal to 0 has no solution, right? Has no solution because m1 is not singular. This is the skew symmetrics. This is the skew symmetric matrix. So m1 is not singular. All right, so if you want, we can compute the determinant of m1 just to make sure it is not singular. So to do so, we can use Cramer's rule, for instance. So that's going to be alpha 1 squared times alpha 2 plus alpha 1 squared times alpha 2. So we have 2 alpha 1 squared alpha 2 minus, all right, on the other diagonal, what do we have? Minus 0, minus 0, minus 0. All right, so that's all we have. And alpha 1, alpha 2, of course, are different from 0. Otherwise, we wouldn't have been able to write these rescaled quantities. All right, so it means that there's a problem somehow, right? So it hints a problem. It's like when you use a regular ansatz, you just push it in, and then you hit a 0 is equal to 1. It means there is a problem somewhere. And how can we address this problem? Well, just see by what m1 could be balanced in the problem. Okay, so we have m1 times phi, we have epsilon m0 times phi, and we also have epsilon lambda times phi. All right, so definitely because M1 and M0 both have the same order of magnitude, the only way to balance M1, of course, is not to use this term, because this one is much smaller than this term, all right? So the only way to balance M1 is to balance it with this, all right? So we need a rescaling. We need a rescaling for lambda, and it is such that epsilon times lambda should be of order 1, all right? In such a way that I can have a balance between these two terms, and we can try to make M1 a little bit more singular than what it is in the unperturbed case, all right? And so to do this, we could for instance say that lambda is equal to lambda tilde, a rescaled quantity, over epsilon. All right, so we have large eigen values. All right, and so let's see those large eigenvalues. What we need to say, of course, is that lambda should be of order 1 to make sure we have a rescaling. Okay, rescaling means lambda different from 0. All right. Okay. So if we introduce this expression for lambda, then let's reconsider the problem. M1 plus, let me just put it this way, minus lambda tilde times I and plus epsilon M0 multiplied by phi is equal to 0. Then with this, we can use regular ansatz. Okay, one for lambda tilde and one for phi. It's going to be phi 0 plus epsilon phi 1 and so forth. All right. So if we substitute them in the governing equation, we could almost write the equations at each order separately already, but let's do it in 2 steps. This is maybe more careful. Lambda 0 tilde I minus epsilon lambda 1 tilde I plus epsilon M0 multiplied by phi 0 epsilon phi 1 is equal to order square. So at leading order, M1 minus lambda 0 tilde I multiplied by phi 0 is equal to 0. This is the unperturbed problem, of course. And at the next order, M1 minus lambda 0 tilde I times phi 1 is equal to, I will push it to the right already, the remaining terms, all right? So I just said we have this multiplied by phi 1, and the remainder should be this multiplied by phi 0. Okay, so on the right, there will be lambda 1 tilde I times phi 0 minus M0 times phi 0. Okay, so we have matrices like this, just to make sure we are fine. Okay, so we can now start solving the problem at the different orders. M1 minus lambda 0 tilde I times phi 0 is equal to 0. That's what we need to solve first. All right, so it means that we need to solve minus lambda 0 tilde on the diagonal elements here. And then here we have alpha 1, alpha 2, alpha 1, minus alpha 1, minus alpha 2, minus alpha 1. And this is equal to 0. All right, so if we want to write the characteristic polynomial here, then we have minus lambda 0 tilde to the third. I'm using again Cramer's rules, right? So we have minus minus alpha square, minus, so we have plus alpha 1 square alpha 2. Oops, I maybe did a mistake earlier. I maybe made a mistake earlier already because it was plus and minus. I'm sorry, I made a big mistake. And well, this is why it's beautiful, right? Actually, M1 is singular. I'm sorry, I was not expecting this. Is singular. Okay, that's part of the risks of the live. And I think I will keep it in the video, so you see that sometimes it's good also to make mistakes and realize that, how we can come back to what we need. All right, so I want to keep just going here first. So we have minus lambda 0 to the third. This one definitely cancels out with this one. This is what we said. Okay, and let's try to be careful. Then we need to subtract. Alpha 2 squared lambda 0. And then that's for this term. And then we need to subtract alpha 1 square times lambda 0 minus alpha 1 square times lambda 0. And then we need to subtract again alpha 1 square times lambda 0. All right, so we subtract it twice over here. And you see that now this becomes clear. We can factor lambda 0 out. And then what remains is lambda 0 square plus 2 alpha 1 square plus alpha 2 square, like this. All right. Okay, and definitely we have three roots. We have lambda 0 is equal to plus or minus the square root of minus 2 alpha 1 square minus alpha 2 square. So most likely this is going to bring us with a complex number. All right, if alpha 1 and alpha 2 are real. And or we have lambda 0 tilde equal to 0. All right, and so this means that we have two large roots. And this means that we have one root of order 1. This is the one I was just trying to shortcut or to bypass earlier. And so it means that I just wrote here, rescaling means lambda tilde is different from 0, but in fact, lambda 0 tilde equals 0 means that there will certainly be a eigenvalue which is of order 1. All right, and so this is the one we should focus on. Okay, so if you want to compute now the corresponding eigenvectors, they might be a little bit tough. All right, so for these two large roots, corresponding eigenvectors are a little long, so we don't compute them. How would we compute them though? That is quite simple. We need to return to the problem here, that we want to solve, we just replace lambda 0 tilde by one of these two quantities. Just keep those along the diagonal elements, like here, multiply this on the right by phi 0, and then solve this problem, all right? But you see that because the expressions we have for lambda 0 tilde is a little bit complicated, although this is not impossible to manage, of course, but it's a little bit more complicated. The expression you'll end up with for the eigenvalues will be a little bit more extended. All right, so we need to focus now on the other root, the one that is of order 1. All right, there's nothing bad in the rescaling we did. It just does not necessarily follow exactly the usual flow. But if we keep going with the next order equation, then for sure we're going to get lambda 1, which is the leading corresponding to the root of order 1. All right, and so let's keep going here. And let's write the order epsilon equation corresponding to the root lambda 0 tilde is equal to 0. All right, so we have m1 multiplied by phi 1 or probably we can get, let's try to make it neat and get the eigenvalue first corresponding to that. All right, so the eigenvalue corresponding to lambda 0 tilde is equal to 0. That's something we should have, or we could have computed earlier. So we have 0. I'm just replacing here in this matrix lambda 0 tilde by 0. So we have just m1 multiplied by xyz, all right, which is phi 0, the corresponding eigenvector, and this should be equal to 0. All right. So how could we do? I don't know. First, let's write the first equation. The first equation says alpha 1 times y plus alpha 2 times z is equal to 0. So definitely z is equal to minus alpha 1 y over alpha 2. So for instance, we could choose y is equal to alpha 2, which means that z is equal to minus alpha 1. All right, and if we go to the second equation just says minus alpha 1 x plus alpha 1 z is equal to 0, which means that x is equal to z. And so the first eigenvector, phi 0, the one corresponding to the eigenvalue lambda tilde is equal to 0. The first eigenvector is minus alpha 1, alpha 2, and minus alpha 1. All right, that's the eigenvector. Okay, so that's in fact something I should already have observed in the unperturbed case, right? Because we're just computing here the eigenvectors of matrix M1, which is singular. It has a 0 eigenvalue, and that's the only one we capture. That's the only one we capture in the unperturbed case. Okay, why? Because the other two eigenvalues are large eigenvalues. Okay, these are the two eigenvalues that we have determined with the scaling, and that we are going to summarize a little bit later. Okay, so coming back to the second equation, we have m1 minus 0, because we're considering just this value here, times the eigenvector phi 1 is equal to the right hand side. All right, times m1 is equal to the right hand side, and what we are aiming for here is the determination of the eigenvalue lambda 1 tilde minus m0 phi 0. All right, like this. Okay, so how do we do that? We just do a projection as usual, right? So we do project, watch out, and this is a big watch out here. M1 is not symmetric. M1 is not symmetric. So it means that we need to compute. So we need to compute the left eigenvector. All right. So let me just give here a short recap on left and right eigenvectors. So we have A minus lambda I x is equal to 0. And then the left eigenvector is y minus lambda I is equal to 0. All right, x and y stand for the eigenvectors, and lambda is the eigenvalue. The eigenvalue is the same, right? So it's shared between the two eigenvectors. And somehow, if you want lambda, x, and y, they form a triplet. Okay, all these three quantities, they go together and they correspond to eigenvalue and then left and right eigenvectors. So if you transpose here the second equation, you see that we have A transposed minus lambda transpose of identity remains identity. Usually we write this y transpose, sorry, multiplied by y, and this is equal to 0. And so if we compare these two equations, this one and this one, we see that in fact the left eigenvector is nothing but the eigenvalue. Okay, this is a standard right eigenvector. This is a standard right eigenvector of the transposed matrix. All right, so let me just write in words. The left eigenvector is the right eigenvector of the transposed matrix, of the transposed matrix. All right, we have things that are quite similar with complex matrices, but I'm just dealing here with real matrices, and that's what you need to keep in mind. All right, so it means that we are looking for the eigenvectors, standard right eigenvectors, I mean, of the transposed of M1. All right, so project here on left eigenvector. But you see M1 transposed, if you want to solve that problem, M1 transposed, actually this is nothing but 0. And then because the matrix is skew symmetric, this is what I said at the very early beginning, you see that this is the transpose of M1. Actually, it's nothing but minus M1, all right? And so instead of solving M1 transposed times y is equal to 0, you see that because M1 transposed is equal to minus M1, it means that the left and right eigenvectors are the same, because it's like solving M1 times y is equal to 0. All right, so this is something really specific. M1 is not symmetric, but because M1 transposed is equal to minus M1, left and right eigenvectors are the same. Left and right eigenvectors are the same. All right. So it means that the projection, in fact, can be done on phi 0. All right. And so what we have here is phi 0 transposed M1 times phi 1, which is designed to be equal to 0. And this is also equal to lambda 1 tilde phi 0 transposed times phi 0 minus phi 0 transposed M0 phi 0. All right, so this is the squared norm of phi 0. And so that's alpha 1 square twice plus alpha 2 square. And then we need to compute this product here. And that product, because M0 is the diagonal matrix, you remember M0 is the diagonal matrix with E1, E2, E3 on the diagonal. we can carry on this product quite easily. And it's going to give E1 times alpha 1 square plus E2 times alpha 2 square plus E3 times alpha 1 square again. And so this means that lambda 1 tilde is equal to E1 alpha 1 square plus E2 alpha 2 square plus E3 alpha 1 square divided by 2 alpha 1 square plus alpha 2 squared. All right, and so as a conclusion, we need to return to the original quantity of the problem. Returning to the original quantities of the problem, we see that lambda, this is how we decided to rescale the eigenvalues, all right, is lambda tilde over epsilon. So we have, in this case, lambda 0 over epsilon, so we have plus or minus 1 over epsilon square root of minus 2 alpha 1 square minus alpha 2 square. All right, this is for the first two roots that we have investigated. And then for the next root, we have lambda tilde 0, which is equal to 0. And then, so we substitute this into the ansatz over here. So this term drops. What remains is just epsilon times lambda 1. So lambda tilde over epsilon, you see here, which is the lambda we need, is in fact equal to lambda 1 tilde. All right, so the other solution is lambda equal to the lambda 1 tilde. That is nothing but the quantity we have over here. Copy and paste. Oops, that's wrong. This quantity over here. All right. And that's pretty it, right? Because the only thing we were asked was to provide the perturbation to the quantities, the different eigenvalues of the problem. And we see in this case, when we have large eigenvalues, large values for A1 and A2, we see that we still have an eigenvalue which is of order 1, the one corresponding to the unperturbed problem, and we have two perturbations coming, which are large eigenvalues to those matrices. All right, I hope it was clear. There was a little bit of a hiccup in between here because I didn't notice that M1 is singular, but you see that we can always come back to what we do expect. Especially, we noticed here that there was a problem because we ended up with the fact that lambda 0 tilde should be a solution of this problem. So meaning that M1 actually is singular, and it became quite clear then afterwards. All right, so I hope you enjoyed, and then keep going with the following videos.